examples. All right, so let's do that. Oh, come on. Go away. Skedaddle. So I'm skipping ahead to my examples. All right, so let's use Green's theorem. Calculate this integral of x cubed dx plus yx dy, where c is the counterclockwise oriented boundary of the rectangle 0, 1 cross 0, 1. This is Cartesian product. In other words, this curve is the boundary of a square. Oh, the pure awfulness of this question without Green's theorem. Do you realize what this problem means without Green's theorem? Do you know what this would be without Green's theorem? You have to calculate the line integral around a square. That means that you have to break up and do 4 separate integrals in principle. Parameterize each side of the square and integrate them one at a time. Add them together. That's how you did this before. Or didn't do it, right? Did I have the decency not to assign you one of these before? I didn't do it to you, did I? I did? Okay, good. I should have done that. Just so you can now go back and use Green's theorem and realize the awesomeness of Green's theorem. So check this out. So what is this? This is P. This is Q, right? So the integral around the boundary, I'll use boundary of R. I like that. Double integral over the unit square of, what do we got? We got partial x of xy minus partial y of x cubed dA, which is what? Integral from 0 to 1. Integral from 0 to 1 looks to me like a y dy dx. Y dy dx, yeah. There's so much you can see from this formula just looking at it. Like, I can immediately see that if I took that vector field, right, and I mean, I could add pretty much any function I want to here of what? Of x. It won't change anything, will it? Because it just gets differentiated with respect to y over here. But anyway, let's get back on track. So this is what? Integral from 0 to 1 of 1/2. So the answer is 1/2. Man, that is nice. Can we use this theorem in the opposite sense? All right, so I've showed you kind of 2 examples where it was kind of nice because the theorem allowed us to trade a line integral we didn't want to do for an area integral, which wasn't too bad. The other way to use this theorem, right? Integral of dA is what? in terms of, so let's see here, look over here. We have the integral of p dx plus q dy over the boundary of some region is equal to the double integral over the region of partial q, partial x minus partial p, partial y. So my question to you is, what could I choose for a vector field as to get the coefficient of the dA in Green's theorem to be 1? There are infinitely many choices. I just want one. How can you make this be 1? Y dx plus x dy. But that will give me 0, won't it? So that would be 1 minus, that would be 0. No sine and cosine. There are a couple options here. That was almost right. You guys are starting to see the right idea. Let me just tell you the 3 popular choices. And then, so you could either use 0x, you could use minus y0, or minus y over 2, x over 2. These are the kind of easy ways to make that. But there's many other choices. I think if I do, so this by Green's theorem, so this should be the area of R. Area of R, right, is the double integral over R of dA, but you know what else it is? It's the integral over the boundary of R of x dy. So we can calculate areas by doing very specific line integrals. For example, applying this, how about the ellipse? Suppose I want to find the area of the ellipse. So I can say the area is equal to the integral over the boundary of the ellipse. In other words, this guy, right, of x dy. How do you parameterize an ellipse? How about x is equal to a cosine theta, y is equal to b sine theta? So that becomes the integral from 0 to 2 pi. My x is a cosine theta. My dy is what? B cosine theta d theta. So I get a, b, integral of cosine squared theta d theta from 0 to 2 pi. Hey guys, observation. The integral from 0 to 2 pi of d theta is 2 pi. And sine squared theta plus cosine squared theta is equal to 1. And you know, sine and cosine, they're the same as far as we consider the whole interval from 0 to 2 pi. So, by symmetry, that integral must be pi. Of course, if you don't like my symmetry argument, you can use cosine squared as 1/2 of 1 plus cosine 2 theta integrate. The sine 2 theta drops out because you evaluate at 0 and an integer multiple of pi, thus giving you 0, and you get pi again. But I think the symmetry argument's fun. Es bueno? See, what was the other way we calculated this was to use the Jacobian argument, make the change of variables, where we got AB from the Jacobian. Right? I think if I use this vector field, maybe you end up with just integral of d theta times AB for this example. I like the two examples I've showed you today so far, but the one I will finish with today, and I better project it so I don't keep you over time. The one I want to finish with today is absolute madness. Let me just set up the problem. Suppose you want to find the area of this, where these are given points, P1, P2, P3, P4, etc., 5, 6, 7, 8, 9, 10, P10. How would you find the area of some sort of polygon? What's that? Green's theorem. Well, why are you in this class? You already know it. Oh, man. I'm wasting your time. Okay, so I said get off. So you can show that the integral of 1/2 x dy minus y dx is equal to 1/2 x1 y2 minus x2 y1, where these are the x and y components. So this is the integral over a line segment that goes from x1 y1 to x2 y2. The value of this particular vector field's line integral along a line segment is simply given by this particular difference of products of their Cartesian components. But of course, you know what we were just talking about is this thing, when you apply it to Green's theorem, gives you area. So if I want to look at the area of some polygon, I can just integrate 1/2 this thing over the boundary of the polygon, which because of this little calculation, that it's not in my notes, but it's easy to work out, you get the integral along each little line segment, which then gives you this particular sum and difference of products of the Cartesian components, which is just bizarre. For example, you can calculate the area of a polygon with vertices 0, 0, minus 1, 1, 0, 2, 1, 3, 2, 1 is 9/2 by applying the Biot formula. Try it for yourself on something that you know, like a square. See how it works. It's really cool. Because you could take a polygon with 1,000 points, and you could still find its area without doing a lick of trigonometry. And that's weird. Anyway, thanks, guys. What's that?
Provided all the sides are straight.
Only what?
Sides are straight.
Yes, we do need straight-sided polygons. Yes. Mr. Gibson is trying to use singular polygons.